Beginning in 2015 and continuing into 2017, maritime engineers ran a mandatory hazard clearance sweep in the Kerch Strait. Before any piling or dredging for a massive civil engineering project could begin, the seabed had to be cleared of unexploded ordnance, 74 years of accumulated wartime metal in a narrow maritime choke point. Contractors worked disciplined diver grids, classifying and neutralizing anything that could detonate under heavy equipment. Inside that rigid protocol, a volunteer search team operating alongside the clearance crews flagged an anomaly resting 30 feet below the surface. The target lay about 6 kilometers off the Taman coast. At that depth, the seabed is a dense silt and sand matrix, constantly worked by strong tidal currents. Working in highly restricted visibility conditions, the diver teams mapped the outline of a massive metallic structure. The object was not a standard naval mine or a localized munitions dump. The anomaly was an intact aviation airframe. It was identified as a Curtiss P-40 fighter from the Kitty Hawk and Tomahawk family, supplied to the Soviet Air Force through the United States Lend-Lease program. The airframe rested firmly on the mud with its nose pointing toward the Taman coast. This find was a direct byproduct of the clearance mandate behind the Crimean bridge work. Heavy equipment cannot enter uncleared mud where buried shells or bombs could detonate under piling loads, so teams move in strict grids, investigate every contact on the bottom, and escalate anything suspicious through an explosive hazard chain of custody. In this corridor, unknown metal is never ignored. That mandate also draws a hard procedural line. These were not aviation archaeologists hunting historical wrecks. They were commercial contractors on a tight hazard mitigation timeline. When the grid produced a fully armed World War II fighter sitting directly in the construction path, the search pattern stopped cold because the corridor could not simply route around it. Under the infrastructure mandate, the aircraft had to be cleared, which turned the recovery into a salvage of opportunity. The priority was to open the seabed for bridge work, not to run a museum-grade excavation. In that shallow, high-energy tidal zone, strong currents constantly push fine sediment across the bottom, burying and re-exposing metal over time. Over 74 years, as that motion shaped the fighter's surroundings and partially locked it into the mud. The crews used the airframe's forward attitude as their working reference, then documented exterior dimensions and the exact resting state of the aluminum skin before any heavy recovery gear could be brought into the sector. The forward hull's alignment and the fact that it still held its shape argued against a steep, catastrophic nose-in impact. With the site fixed inside the clearance grid, the next step was not speculation but reading the airframe itself. What condition was it in, and what sequence of events put it here? The airframe's geometry on the seabed was a clue, not a courtroom verdict. Its nose still pointed toward the Taman coast, a heading some investigators have linked to a last attempt to reach friendly shoreline in 1943. In the fighting over this region, the aircraft may have taken combat damage. Some accounts point to ground fire, leaving the pilot with fewer options as power and control bled away over open water. Bailing out of a severely damaged fighter at low altitude carries extreme physiological and mechanical risk, especially over a heavy marine choke point. The alternative was flying the deteriorating airframe down to the surface of the Black Sea. The pilot chose to execute a controlled water ditching. A Curtiss P-40 Warhawk is far from an ideal aerodynamic shape for a water landing. It is a dense, heavily armored front-heavy machine built entirely around a massive liquid-cooled Allison inline engine. Bringing the specific airframe down on a moving sea state requires absolute precision. The pilot must manage the decaying airspeed and heavy flight controls to avoid instantly tearing the aircraft apart upon contact with the dense water. The real constraint is kinetic energy. The instant a heavy, front-loaded fighter trades air for water, the sea becomes a brutal brake. Drop the nose too early and the engine bites, flipping the aircraft end over end. A controlled ditching keeps the nose up at the edge of stall while the belly and broad wing undersurfaces skim in first, bleeding speed horizontally across the surface over several hundred yards. Done well, it prevents immediate fragmentation and keeps the cockpit above water just long enough for an emergency exit. The seabed evidence read more like a controlled water landing than a steep, catastrophic impact. A cartwheel, a sharp nose-first strike, A high downward angle would more likely have crushed the cockpit, torn mounts, and scattered wreckage into a wider debris field. Instead, the forward fuselage, cockpit enclosure, and wing roots remained integrated, with the surrounding skin and framing largely holding their shape, strong indicators of a managed arrival, best treated as provisional until a detailed forensic assessment can test the story the structure seems to tell. After shedding its forward velocity, the heavy engine block inevitably dictated the sinking mechanics of the airframe. The aircraft rapidly lost buoyancy as water flooded the engine cowling and the lower fuselage sections. Within moments, the dense fighter pitched nose down and began its descent through the water column, sinking 30 feet down to the dense silt of the strait. It settled exactly on the heading the pilot had steered during the final approach. The heavy fighter locked firmly into the seabed, leaving the aluminum airframe in its final orientation for over 7 decades. The structural integrity of the submerged cockpit meant the immediate physical environment around the pilot seat was perfectly protected from the initial crash forces. The aluminum structure clearly survived the violence of the ditching, leaving a critical procedural question regarding the ultimate fate of the pilot who executed the landing. The cockpit survey raised an immediate tension in the evidence. Divers documented an unused flight parachute near the pilot's station and a camera inside the cockpit area, while the airframe still carried its full forward armament, 650 caliber Colt Browning machine guns integrated into the wing roots. The guns confirm the fighter's lethal design and interceptor role, but a camera can point to phototasking or a field modification without automatically redefining the aircraft as a dedicated reconnaissance platform. Without unit logs and technical identification of the installation, the narrow conclusion is safest. This flight carried photographic equipment, and its precise mission profile remains uncertain. The most critical piece of forensic detail was reported inside the cockpit, a packed parachute associated with the pilot's station. In a loss at sea, a parachute found with the aircraft can suggest the pilot did not bail out at altitude, but it cannot, by itself, prove what happened in the seconds after touchdown. It narrows the possibilities without closing the case, leaving the pilot's fate as a question that must be answered by records, identification, and corroborating evidence, not a single artifact's position. The survival of a delicate fabric parachute underwater for over 7 decades requires highly specific conditions, and even then it is survival by slowing decay, not stopping it. Soon after the aircraft settled, fine sediment could have infiltrated the cockpit and partially buried the interior, reducing water flow and limiting oxygen in pockets of trapped mud. In low-oxygen microenvironments, corrosion and biological breakdown can proceed far more slowly, and organic materials may persist longer than expected. But the exact degree of preservation depends on the fabric type, its salt content, and how completely the artifacts were sealed. Because of those low-oxygen, silt-sealed conditions, the teams did not find a stripped aluminum shell. They found a mechanical time capsule. Alongside the parachute and the camera, the mud protected the engine block, the main pilot dashboard, and the heavy pilot seat. Even firing mechanisms and ammunition feeds for the 650 caliber weapons remained structurally intact beneath the dense silt, which also shielded delicate parts from the grinding abrasion that usually destroys shallow water artifacts. What divers could visually verify inside the forward fuselage provided a rare, coherent forensic snapshot, not an airtight verdict. The preserved cockpit layout, the intact armament, and the presence of photographic equipment can narrow possibilities and suggest a flight that carried more than a routine gun loadout, while the airframe's condition supports the case for a controlled ditching executed under pressure. But the pilot's exact mission and final fate still require records, identification, and corroboration beyond the placement of a few surviving artifacts. The commercial divers systematically documented these internal elements, maintaining rigorous evidence discipline despite their lack of specialized archaeological tools. However, the state civil engineering mandate required swift verification and immediate removal. The entire intact airframe still physically blocked the primary construction corridor for the immense infrastructure project. The initial interior survey phase was now complete, and the artifacts proved the immense historical value of the site. With the internal evidence perfectly documented, the operational focus abruptly shifts to the massive mechanical problem of separating the heavy aircraft from the gripping mud of the seabed. Over roughly a week, commercial dive teams rotated through long shifts to free the embedded fighter from the bottom. They excavated compacted sediment from around the fuselage, exposed safe structural pickup points, and routed lifting slings with methodical care under the project's safety rules. Extracting an intact aircraft from the sea introduces severe mechanical hazards, especially for a semi-monocoque airframe like a Curtiss P-40 Warhawk. In that design, the outer aluminum skin is not cosmetic, it is load-bearing, carrying and distributing stresses into bulkheads and stringers. After more than 70 years in salt water, galvanic corrosion thins panels and weakens rivets, stripping away the structure's original stiffness. Under lift, uneven strap pressure can turn that compromised skin into a failure point, crushing or tearing where the load concentrates. This structural vulnerability is severely magnified by a hidden environmental factor. While the dive team successfully cleared the exterior mud to pass their straps, the enclosed interior of the airframe presented a massive, uncalculated mechanical burden. Over the course of 7 decades on the seabed, the continuous tidal currents forced extremely fine marine sediment into every open cavity of the fuselage. Silt steadily infiltrated the empty ammunition bays, the complex control cable runs, and the deep structural voids within the long aft tail section. Over decades, that silt did more than infiltrate. It packed the fuselage, displacing seawater with dense, saturated sand and clay. Trapped inside enclosed bulkheads, it could add several unpredictable tons and drag the center of gravity far aft of design limits. Without a full-length recovery cradle, the team had to sling the aircraft under the wing roots and forward engine mounts, leaving the sand-filled tail to hang as a heavy lever arm. The result was unavoidable. Every strap became a concentrated point load pressing into weakened aluminum. The physical geometry was carefully prepared over a 7-day timeline of intense underwater labor. The heavy lifting slings were locked firmly into place around the forward fuselage. The detailed site preparation and hazard mitigation phases were now completely finished. The divers cleared the water column entirely, but the ultimate test of the degraded airframe will occur at the exact moment of vertical extraction. The decision to utilize a massive floating construction crane permanently dictated the outcome of the vertical extraction. Positioned securely over the restricted coordinate, this heavy marine derrick was diverted directly from the Crimean Bridge civil engineering fleet. The operational trade-off at this moment was absolute and procedurally necessary. The surface coordinators exchanged the delicate, balanced control of a specialized aviation lifting frame for the immediate, overwhelming hoisting capacity of a bridge-building asset. Because the operation was strictly a salvage of opportunity, as the primary mandate remained the rapid clearance of the physical construction corridor. The heavy derrick lowered its primary mechanical hook through the 30 feet of water to meet the centralized rigging straps previously secured by the commercial dive teams. As the powerful winches engaged on the surface, the thick steel cables pulled perfectly taut. This motion instantly transferred a multi-ton lift load, complicated by trapped mud and water, directly to the central lifting points. This direct application of vertical lifting force through centralized straps created a severe structural risk. Hoisting a long, narrow aluminum airframe from near its middle without a full-length support frame can concentrate bending loads across weakened sections, especially after decades of corrosion and sediment intrusion. Some accounts of the lift describe parts failing or separating under stress. Other contemporary reports describe the fuselage coming up with the wings and part of the tail still attached. What is clear is that the operation prioritized corridor clearance over museum-grade extraction, and the ascent through the water column would have imposed punishing drag loads on any broad surfaces still connected to the core structure. When the crane finally broke the surface, the recovered assembly was swung over and lowered onto a waiting transport barge. A successful clearance for the engineers, but not a controlled conservation lift. The physical evidence recovered to the deck of the transport barge provides a definitive accounting of the extraction. We can firmly verify that the heavy inline engine, the primary cockpit enclosure, and the forward wing roots survived the ascent to the surface. Conversely, the structural aft section and the outer wing panels remain permanently lost to the seabed, leaving only the densest core of the fighter plane available for historical preservation. With the fragmented airframe resting securely out of the water column, the engineering teams initiated an immediate baseline inventory. The civil contractors needed to document exactly what was successfully removed from the construction zone before transferring the materials to local authorities. The dense forward assembly retained a tremendous amount of verifiable mechanical data. The recovery team successfully secured the main pilot dashboard, the heavy armored pilot seat, and the complex flight control linkages still mounted within the forward bulkheads. Alongside the intricate flight controls, the aggressive forward-firing armament remained fully integrated into the surviving wing roots. 6 50-caliber machine guns, complete with their intact mechanical ammunition feeds and heavy mounting brackets, were systematically logged and stabilized on the steel deck. The physical survival of these specific combat components was directly tied to their heavy, localized armor protection. Once on deck, the recovered aluminum and steel core posed an immediate handling problem simply because of its mass. As water drained from internal voids, saturated clay still clung inside the cowling and around the engine block, and crews had to clear it before any meaningful weighing. And contemporary reports put the dry recovered assembly at more than 3.5 tons, roughly 7,700 pounds, a forward heavy block built to absorb vibration and recoil from the 6 machine guns. For over 7 decades, it had also sat in an oxygen-starved pocket beneath the mud, a barrier that slowed rapid oxidation until the moment it met open air. However, the moment the heavy structure broke the surface and interacted with atmospheric oxygen, the accelerated decay cycle instantly resumed. The high concentration of marine salts embedded deep within the aluminum overlapping joints began immediately reacting with the open air. To halt this aggressive degradation, the recovery coordinators required an immediate, localized stabilization protocol. The entire exposed assembly had to be systematically flushed with fresh water to strip away the highly corrosive chlorides. Surface teams utilized high-pressure hoses to wash the heavy marine mud from the delicate instrument panel, the pilot seat, and the engine exhaust manifolds before the aluminum skin could dry out and physically blister. The mandated civil engineering clearance of the restricted maritime corridor was now procedurally complete. The previously blocked seabed was fully verified, cleared of all metallic obstructions, and officially open for the heavy bridge construction pilings. With the operational hazard timeline thoroughly exhausted, the civil bridge engineers transferred the physical chain of custody directly to state historical authorities. The recovered assembly was reported to have been taken to secure staging at the Kerch Fortress, where it could enter long-term conservation to slow further decay and prepare key components for public display. Plans described the artifacts being mapped, cleaned, and stabilized for static exhibition at a local coastal battery museum site, an intended outcome that depends on conservation capacity and official curation decisions after the recovery.